How will Milankovitch cycles impact the Earth? Imagine a future where vast regions of the planet are covered in ice, entire forests buried under thick snow, or, conversely, where deserts expand, swallowing fertile lands, and extreme heat becomes the new norm. These dramatic shifts in Earth's climate aren't just caused by human actions, but by powerful forces that have shaped our planet's fate for millions of years. In today's video, we'll explore these forces and how they might quietly set the stage for ice ages or intense warming periods. Stick with us to discover how Earth's future could be radically different from what we know today. The Milankovitch cycles are periodic variations in Earth's orbit and tilt that occur over thousands of years, influencing the planet's climate. There are three main cycles: eccentricity, which alters the shape of Earth's orbit; obliquity, which refers to the tilt of Earth's axis; and precession, which is the change in orientation of Earth's axis. These cycles affect how much sunlight Earth receives, which in turn influences climate patterns such as ice ages and interglacial periods. The first, Earth's orbital eccentricity, refers to how our planet moves around the Sun. Instead of tracing a perfect circle, Earth's path is slightly oval, or elliptical. This ellipticity varies over time, making Earth's orbit sometimes more elongated, sometimes more circular, over cycles lasting about 100,000 years. This is one of the variables that influence the planet's climate over geological eras. When Earth's orbital eccentricity is greater, making its trajectory more oval, there are periods when the planet is farther from the Sun during its annual revolution. This can result in colder winters and hotter summers in certain parts of the world, depending on interactions with other climatic factors, such as Earth's axial tilt and precession. Conversely, when eccentricity is less, the orbit becomes more circular, leading to a more uniform distribution of solar radiation throughout the year, which can smooth out seasonal variations. Earth's obliquity refers to the tilt of our planet's axis relative to its orbital plane around the Sun. Currently, this tilt is about 23.5 degrees, but it's not fixed and varies over time, oscillating between about 22.1 and 24.5 degrees, in cycles lasting approximately 41,000 years. This axial tilt is responsible for the seasons we experience, as it determines the amount of sunlight reaching different parts of Earth throughout the year. When obliquity is higher, meaning Earth's axis is more tilted, seasonal differences become more pronounced. During summer, the hemisphere tilted toward the Sun receives more direct sunlight, resulting in higher temperatures and warmer summers. Similarly, during winter, the same hemisphere tilts away from the Sun, receiving less sunlight and hence cooler temperatures, leading to harsher winters. This increase in seasonal variation can significantly affect ecosystems and human activities. On the other hand, when obliquity is lower, Earth's axial tilt is reduced, and seasonal differences become less extreme. This results in milder summers and winters, with more moderate temperatures throughout the year, which can benefit some regions globally. Earth's precession refers to the slow, gradual movement of the planet's rotation axis, akin to a dance or a wobble that the axis performs over thousands of years. Specifically, precession describes how Earth's axis orientation changes relative to fixed stars, completing a full cycle every about 26,000 years. This movement is caused by the gravitational interactions of the Sun and Moon with Earth's equator, exerting a force on Earth's axis. This precession movement significantly affects the climate and seasons over time. As Earth's axis slowly changes direction, it alters the point in the annual orbital cycle when each season occurs. For example, currently, the northern hemisphere experiences summer when Earth is farthest from the Sun, but due to precession, thousands of years from now, summer will occur when Earth is closest to the Sun. This could result in hotter summers and colder winters, or vice versa, depending on the phase of the precession cycle. When summer occurs near perihelion, the point in Earth's orbit closest to the Sun, Earth receives more solar radiation, intensifying summer temperatures. Conversely, when summer occurs near aphelion, the point farthest from the Sun, temperatures tend to be more moderate. Although slow, this phenomenon contributes to long-term climate variations. Who studied the cycle? The Milankovitch cycles were studied and popularized by Serbian mathematician and astronomer Milutin Milankovitch. He developed his theory in the early 20th century, with his ideas published in 1920. Milankovitch combined astronomical calculations with climate data to understand how variations in Earth's orbit and tilt could influence ice ages and other climate cycles over thousands of years. Before Milankovitch, other scientists had observed that changes in Earth's orbit could affect the climate. But it was Milankovitch who systematized these cycles and mathematically demonstrated how these orbital variations could be correlated with Earth's climate patterns. According to the current phase of these cycles, the planet should be slowly moving toward cooling, which could culminate in the start of a new ice age in thousands of years. These cycles, which include variations in eccentricity, obliquity, and precession of Earth, influence the amount and distribution of sunlight reaching the planet, being crucial for controlling global temperatures over geological timescales. However, human activities, particularly the burning of fossil fuels, have introduced a new and powerful factor into Earth's climate equation. Greenhouse gas emissions, such as carbon dioxide, are warming the planet at a much faster rate than Milankovitch cycles could induce. This accelerated global warming is, in a sense, canceling out the cooling effects that the natural cycles should be imposing, leading to a steady rise in global temperatures, melting of polar ice caps, and significant climate changes felt worldwide. The polar regions, such as the Arctic and Antarctica, are particularly sensitive to changes induced by both Milankovitch cycles and anthropogenic global warming. Small variations in sunlight due to orbital changes can have major impacts in these areas, causing the growth or melting of ice layers. Currently, the Arctic is experiencing accelerated melting, driven by global warming. However, in the long term, if greenhouse gas emissions are controlled, the natural cycles could potentially contribute to a temporary increase in ice layers, depending on their phase. Siberia and Canada, with their vast areas of permafrost, are also highly vulnerable to these changes. The thawing of permafrost in these regions is already being accelerated by global warming, releasing large amounts of methane, a potent greenhouse gas, which in turn exacerbates warming. However, the Milankovitch cycles, over thousands of years, could potentially influence the recovery of these frozen areas if Earth enters a prolonged cooling phase. Still, the effects of human action on the climate may hinder the full recovery of these regions. Finally, the tropical and equatorial regions, although less directly impacted by Milankovitch cycles due to their geographical position, can still experience indirect effects of these changes. Alterations in monsoon patterns, prolonged or intensified droughts, and variations in rainfall distribution are examples of how the cycles can affect these areas over millennia. A curious fact about the Milankovitch cycles is that they played a crucial role in forming Earth's ice ages. One of the most notable examples is the period known as the Ice Age, which occurred about 100,000 years ago. During this time, large parts of North America, Europe, and Asia were covered by thick ice layers, up to 3 kilometers thick in some areas. This massive ice mass formed partly due to a specific combination of Milankovitch cycles that resulted in cooler summers, allowing snow accumulated during winter not to melt completely and build up over millennia. So, did you enjoy learning more about the natural forces that can transform Earth's climate? These changes may seem distant, but their effects could directly impact the future of our planet and our civilization. If you liked the video, don't forget to leave a like, it really helps the channel grow. And to not miss the next videos about the universe, science, and Earth's mysteries, subscribe to the channel and hit the bell to receive all notifications. Also, check out our video about recent discoveries that have advanced archaeology. See you next time.